Hello everyone, John Magyar with Altium, and I'm going to be talking about how to make your product fit that unusual shape. If we look back not too long ago, even just a couple decades, typical PCB design shapes were very simple. Rectangular boards that ended up in some type of rectangular box, plastic or sheet metal, and that's what most consumer products consisted of. And in that case, the PCB influences the product shape. However, today, with advances in mechanical design tools and advances in injection molding plastics, the shapes start to then dictate the PCB design. So let's take an example of a fitness tracker, something that's very form-fitting, worn on the wrist, a lot of electronics, all packed into a very tiny space. Something like this would have a more complex structure for the PCB. In fact, it would be multiple PCBs interconnected with some type of flexible material and occupying a space with very little room left over. This creates some challenges for the PCB designer. So one of the main challenges would be how to get the accurate board and flex shape to start out with, and then how to get the board and flex alignment so that when you start putting components on the boards, how do you do the third issue, which is interference checking? How do you accurately take all of these mechanical constraints due to this small form factor and solve that problem of doing the board layout? So let's take a look at a real example. Here I have a fitness tracker that I will take apart. And to show you the complexity of this is a very powerful device. And here's the bottom or top enclosure piece, and that has an LCD display. On that display, there's some flexible connection here. Flex with a small PCB that contains the touch sensor device, so the touch screen electronics that's embedded right on there. And that connects up to a main board, and the main board has a rechargeable battery unit, a real-time clock battery unit, some power management, and that's a small rigid board connected through some flexible connection to the main board, and the main board is where it's all happening. Here's the this has quite a bit. It's a 32-bit processor with some flash memory, and it has a GPS module, and it has Bluetooth and wireless connection. So there's quite a bit going on in this system that all needs to be packaged very compactly for it to fit on the wrist. So let's say 3 printed circuit boards here and very compact. How do we go about this challenge of doing board layout and making something like this? So let's look at the challenges again. So board and flex shape and board and flex alignment. So these two problems can be solved by borrowing heavily from the MCAD domain. When a product such as this is designed, there's a mechanical team which undoubtedly would start out with the overall form of the product. The information they produce can be borrowed and brought into the electrical design domain. So their assembly, the top and bottom piece, and their modeling of the bare boards within the assembly can be leveraged. You can take that information, import it as step format, and then you can tell the design tool, I want this particular board to have this shape, and you can point to a specific model and say, make the board this shape. So that's how you can get your complex, irregular shapes taken care of. Regarding the alignment, if you bring that same assembly in its final state, it preserves all of that positioning. So you can have your boards aligned relative to each other and the enclosure. And when you make your PCB shapes, you can make them occupy that same space. So therefore, the alignment of everything is preserved. And then you can worry about the third problem, which is interference checking of components that you're going to place on these boards and the other boards themselves interfering with each other or the enclosure. So once you have that mechanical data imported in, the PCB design process is just as it is, where you worry about placing components and you let your design rule checks take over and leverage that mechanical information as the DRC boundaries of where you can place components and where you can't. So a very challenging problem, but again, borrowing from the MCAD domain, you can solve this and produce a board with minimal mechanical respins when you hand off the final electronic assembly. If you have any questions about this topic, please drop them in the box below. And thanks for watching.